Welcome back. So we are going to look at today second order systems. If you haven't watched first order systems, which is the previous video on the playlist, advanced control systems, you should watch it first. I also did several examples there. Before watching that video, if you watch second order systems, you can still survive, but it is about a uh, 12 to 15-minute video. So for first order systems, you should watch it first. All right, we are looking at second order systems very common. We deal with second order systems in engineering, especially if you are like me working on robotics, ground vehicles, aerial vehicles. You can approximate them very closely as a second order system. And even if you don't have a second order system, after applying a feedback linearization or a state transformation approach, you may end up having systems of this form. And in my channel, there are examples about that at different playlists. So if you have difficulty finding feedback linearization or state transformation, let me know in comments and I will guide you to the related videos. So, as I mentioned, this type of system pops up from multi-agent systems when we design higher level motion planning algorithms. They can represent also decoupled aircraft responses, pitch, yaw, and roll. Um, we approximate quadcopter dynamics like this when we control each axis plus the altitude. Forgetting about robotic systems and aircraft responses, the general structure of RLC electrical circuits, if you're an electrical guy, not mechanical or aerospace, these systems are also very common and very popular on the motion control domain. All right, I'm going to look at first, similar to the first order systems case, I'm going to look at first controller, which is good at following a constant command C. C is the constant command. Sometimes I refer to as the trajectory, set point, so on and so forth. It goes with different names, command C. When I have this type of a controller, by the way, I don't want to ruin the surprise, but if you are dealing with a second order system like this, K1 and K2 are always positive, but let's say you don't know this. First of all, when you have a system like this, I would like to go to state space to analyze. We did several examples how we can go from differential equations to state spaces. Once again, if you had a hard time finding those videos, let me know. So, assuming you know how to go from ODEs to state space representations, just call x1 as the x, x2 as the x dot. Then you differentiate x1 dot, x1 dot becomes x dot is x2, so x1 dot becomes x2, and x2 dot, if you differentiate x dot dot, what is x dot dot is u, so x2 dot becomes u. So if you denote the state vector as x1 and x2, then you can write the same system that you see on the top into the state space form 0, 1, 0, 0, and 0, 1. So when you close up the system, when you close, basically once you apply this type of a control structure, right now x is x1 and x dot is x2, I am assuming x dot is available. You can think this as the position, this as the velocity state of my system. Like the state feedback case, all the states are available to me. Um, if not, you can also use observer, watch the output feedback case, couples videos back. Again, I am covering first and second order systems since they are very popular. Uh, Earlier in this advanced control systems playlists, we covered any system, any linear system, not necessarily in particular form, how you can design general controller types. So for this first and second order systems, I would like to dive a little bit more in detail on specific control structures for those systems. And then I would like to give you a feeling how we design controls. Anyway, so when you close the loop, basically you are applying to this system A and B a control structure like this. So your closed loop system, once you apply U, after minor mathematical steps, you end up having this equation. Since you injected U, Now C becomes X like the comment to this system, and this becomes our new closed system matrix A. And we know a fact. If you have a system like this, if C is constant, if your now C is acting like an input to your closed loop system, and if this is Hurwitz, meaning that if the eigenvalues of that system lies on the left half plane and C is constant, then the states x1 and x2 will converge to their equilibrium points. That's a fact. Once again, if you have a system like this, not necessarily second order, any linear system looking like x that equals to ax plus b, C is constant. If this Hurwitz system will converge to its equilibrium points. And if you analyze the equilibrium points by setting x dot to 0, from the first row, 0 equals to x2 plus 0. So really you have x2 equals to 0 from the first row. So equilibrium point for the second state, let's say velocity is 0. Which makes sense, right? So because once your position approach to a constant command, then your velocity stops. You converge from, think about altitude regulation. So you want your quadcopter to go from 0 to 5 meters. When quadcopter goes to the 5 meters, it stays there. Its velocity on the altitude axis doesn't move. So velocity becomes 0. Now, equilibrium analysis wise, if you look at the second equation, 0 equals to minus k1 x1 minus k2 x2 plus k1 c equals to 0, left hand side. So x2 was 0 from the top. We end up having minus k1 x1 plus k2 k1c. So if you divide both sides by k1, so x1 equals to c. So equilibrium points for x1 is c and x2 is 0, meaning that if you make this Hurwitz, your position state will follow the command and your velocity will go to 0, which does our job with, your position state x will track the constant command with this controller. Yay. So now how you can make this Hurwitz, again, we did several versions of this earlier in this playlist, Advanced Control Systems. You take this A matrix, you take this B matrix, in this case, 2 by 2 Q, 1 by 1 R, pick Q and R, and any positive definite Q and R will do the job. I'm not talking about convergence, but it will make closed loop system stable. Then you can tweak QNR to achieve a desired level of convergence if you are dealing with such a system. All right, so you may prefer a Lyapunov version of the analysis, which is fine. I would, if you don't want to use the fact that I just showed you, because it won't generalize when we have the time varying comments. So I would like to cover it a little bit. I am denoting E1 as the x1 minus c. My main goal is to drive x1 to 0. E2 becomes x1 dot minus c dot. X1 dot, if you remember, x1 dot is x2. So really we have E2 is x2 since c dot is 0, constant command. So E2 is x2. Don't forget that. So E1 dot becomes, if you take the derivative of the first one, since I am trying to form the aerodynamics, E1 dot becomes x1 dot minus 0. X1 dot is x2, or E2. I should have written E2 here since they are the same. And E2 dot is x1 dot dot. If you insert x1 dot dot, which is x1 dot dot is u, minus k1 e1 minus k2 x dot was x2, and x2 was E2. That's why you have this dynamics. Now, if you use this Lyapunov function candidate, k1 over 2 e1 to the power of 2 plus 1 over 2 e to the power of 2, with k1 being positive. I mentioned k1 and k2 for the second order case will always be positive, but still I need to write here, mathematically speaking, I need to be mathematically accurate in everywhere. So this must be positive, definite, radially unbounded. When e1, e2 equals to 0, it is 0. So this is a valid Lyapunov function candidate. I take the derivative. Some terms will cancel out. You can pause the video. Really not hard. but eventually you end up having, you started with two variables, E1 and E2. Unfortunately, you have only one of them. You know, it is like you went to a trip with your friend, but your friend is missing. And you know, when friend is missing, something is wrong. You cannot claim asymptotic slash exponential stability. The best bet at this stage is to have Lyapunov stability, because E1 to the power of 2 type of a term is not there. You just have E2 to the power of 2, assuming K2 is positive definite. And here we just show Lyapunov stability means E1 and E2 are bounded, but that's really what we want. We want E1 to go to 0 and E2, our velocity error, to, to vanish as well, right? Your velocity will vanish because E2 was x2. So we would like to further analyze this Lyapunov analysis by recalling Lassalle's invariance principle. Lassalle's invariance principle looks at what happens when V dot is 0. So V dot is 0, my energy stops when E2 is 0. So now when E2 is 0, E2 dot is 0. Now I am taking this equation, I am going to insert E2 0 from here, and E2 dot equals to 0, which means E1 equals to 0, meaning that this V dot becomes identically 0 only when E2 is 0 and E1 0, which is perfect because I dissipate energy when I lie on my bed, meaning that I sleep. So at my equilibrium, when E1 and E2 goes to 0, then that's where I dissipate energy based on Lassalle's invariance principle. Thanks to it, we show both E1 and E2 goes to 0, meaning that x1 will track the constant comment, and E2, which is x1 dot, my velocity will vanish as expected from the previous analysis. A different version. I just gave you the Lyapunov version. So now for the first case, if you have watched first order systems controller type 1 to track constant comments, I give a numerical example. I am not going to give another numerical example for the case of second order system, but I do give an example for this type of a controller, which is good for tracking time varying comments. You know, you can just, you will see the code momentarily. You can take the code, clean, set c to a constant, c dot 0, c dot dot 0. So you can use this controller. You can basically get this controller for the spatial case, for the case when the command is constant. So you can use the same simulation. Anyway, so this is the generalized case, which is good for tracking. I don't want to say any time varying function. I would like to say any smooth time varying function C, because you need to compute C dot and C dot dot for this analysis to hold. And this control structure assumes C dot and C dot dot are available. If not, like we did for the first order case, we're going to approximate them. But for a second, let's pretend C and C dot and C dot dot are available. Let's say they are constructed using some splines, some radial basis functions, some motion planning algorithms, so that you have a smooth C. You can numerically take its derivative and 2 times to get C dot and C dot dot. So in this case, control design, nothing will change. Design gain K as in case 1. Nothing will change from the stability point of view, because C dot, C dot dot are generally bounded commands. Once you choose K1x, K2x dot, like we did before using, like, for example, you can use linear quadratic regulator. You can also use pole placement here. I forgot to mention. This is just an example. You can basically get K1 and K2, and using the same Lyapunov function in this case, you are going to arrive the same Lyapunov stability than by using Lasalle. You can, for the case of time varying C, you can still show E1 and E2 goes to 0. As this being said, I didn't wrote it here explicitly for the case 2. E1 has this form. E2 is also x1 dot minus c dot, but of course c dot won't be 0 for the case of time varying comments. So it will cancel out with this. C dot dot will cancel out with other terms. You can do the derivation. It is not hard. It is a slight extension for a similar case that I did for the first order systems. If you have any trouble, again, leave a comment. I will explain. So to make this long story short, this controller will do the job. It will track any arbitrary command. Before I move into this part, which is the case when C and C dot dot are not available, let's assume they are available. And we have this controller type here. And we have C, which is sine 0.8t. I need to compute DC, DDC, C dot, and C dot dot, which are I analytically compute like this. I am injecting here. I am using this K1 and K2 control parameters. You can try other potential parameters you can design using LQR. Pole placement, if you would like to randomly pick, K1 penalizes position, K2 penalizes velocity. I tend to use 2-to-1 ratio, 4-to-1 ratio in practical vehicle domain application for ground and aerial vehicles. Sometimes 6-to-1, 6-to-1.5, which reduces to 4-to-1. So you can try 2-1, 4-to, 8-to-8 for different combinations. Generally, this is larger than this guy. Initialization doesn't matter. You can simulate this for any initial conditions. But anyhow, this recording and the plotting routines, if you run this code for this second order system, you are going to get this result. After a couple of seconds, you perfectly track this red dotted time varying command. This is X1. I am just showing the X1, the position state, not the velocity X2. And this is your control signal. But now the question is, what happens if C dot and C dot dot they are not available? For example, I gave this example. So if you watch first order systems video, I will give the same example. So sorry for the repetition, but I think it is necessary. So let's say I am a pilot and I am generating C. It is not pre-recorded. And let's say I am flying and there is a tree. I need to go left and right. So I need to go on the fly. This is a real-time command. And let's say I am, my joystick, they are measuring which commands I am applying. And let's say you have measurement noise. So if you have measurement noise, and or if a pilot is generating this command in real time, meaning that C is not pre-computed like in here, then because of the noise and because of this real-time computation of command based on pilot's feedback, you may not get C and C dot and C dot dot. In this case, similar to the first order systems case, slight different. I am using a low pass filter, but now the low pass filter is a second order low pass filter. And it has a very specific form. I will explain lambda 1 and lambda 2. And here, lambda 1 multiplied by lambda 2. This is plus and this is. The reason I select its gains like this, if you compute for any positive lambda 1 and lambda 2, if you find a transfer function for this low pass filter, you are going to get two real eigenvalues or two real poles. Which is, since you have real poles, not complex, you are not subject to oscillations. And for example, you can also do this for eigenvalue assignment. When lambda 1 and lambda 2 are large enough, then this transfer function will have two eigenvalues or poles that are further on the left of the complex plane, meaning that you can closely approximate this command. This mu will closely approximate this comment. So instead of using C dot, C dot dot, you are going to use mu dot, and mu dot dot. Here, only C is available. I am passing it through a low pass filter, and instead of the comment, I am using mu dot, and mu dot dot. I am not using C dot, C dot dot, because I am assuming I don't know them because of the measurement noise or a pilot, whatever the reason is. Now you can ask, well, everything is great. When lambda 1, lambda is large, I can approximate this comment, yes. But in code, how you can get mu dot and mu dot dot, especially mu is trivial, like at the state. So in the code, you need to write this in the state space form. Let's call it mu1 to be mu2 to be mu dot. Then mu1 dot becomes mu dot is mu2, and mu2 dot becomes mu dot dot, which is the right-hand side of this equation, but instead of mu dot, I am using mu2, and instead of mu, I am using mu1. So this is the equation. And here, one more time, in code, you are not going to use this continuous time equations. You are going to approximate using several methods. Here, I am using first order Euler approximation for each I, mu I 1 and 2, the new value of mu minus the previous value divided by delta. This delta is related with your implementation frequency of your microprocessor or processor. For example, if you can implement the code in 200 hertz, then delta becomes 1 over 200, which is 0.005. If your implementation frequency is 1000, then this lambda becomes 0.001. So anyhow, how you code this in code is, after applying this, basically, if it is not hard to see, take this, make its left-hand side equals to this, you are going to get these two equations. Likewise, instead of mu2 dot, approximate its left by this, and make it equal to the right-hand side, then you are going to get these two equations. If it is hard to see, pause the video, do what I suggested, take this, put to their left-hand sides for mu I equals to 1 and 2, you are going to get these two equations. In other words, it is right-hand side, the mu1 becomes mu2. The new value of mu1 is the previous value plus that lambda multiplied by mu2, which is d mu1. D mu1 is one symbol, likewise d mu2 is one symbol here, which represents the right-hand side of this equation. So the new value of mu2 is the previous one plus this delta multiplied by this right-hand side. Basically, this is what you implement in code. So for d mu2, use this, basically this one, mu dot dot, use this for mu dot dot, use d mu1 for mu dot, and use the new value of mu1 plus for mu, such that, you know, instead of using c dot dot, you can just use mu dot and mu here like this, based on this low pass filtered approach. So I already covered this for the case when C and C dot are available. So I will pass that part. I am assuming I have the same C, but I for some reason I don't know C dot and C dot dot. I already explained to you. I am implementing this low pass filter procedure, which is exactly like this. When you do this, you need to initialize that low pass filter. Yeah, I usually select 0 almost all the time. And this is the control signal. Unlike the previous one, C dot dot, we are not using them. We are using mu1, which corresponds for mu dot and mu dot dot. And this is the same system, same recording procedure, same plotting. First, I am going to show the result when lambda 1 and lambda 2 they were 2. Well, this is the actual command in red. We are tracking it, but with some lag because of this low pass filter, could not able to approximate the actual command well. But when you increase those gains to, let's say, 20, you can perfectly, not perfectly, but almost perfectly track this command. You can compare this with the case when C dot and C dot dot are available. It is not that perfect, but close enough. Engineeringly, you can track any time varying command without knowing C dot and C dot dot. If this creates a problem for you, if not, you can use the first algorithm that you see if C dot and C dot dot are available to you. All right. So for first order systems and second order systems, we covered controllers to track constant or time varying commands with some smoothness properties. For the first order case, C dot needs to be available if you are not using low pass filter to approximate. And for the second order case, C dot and C dot dot available if you are not approximating by some low pass filter. The third approach that I haven't covered for first order systems, because to be honest with you, if I am dealing with a first order system, I usually don't use this integral approach because first order systems are relatively simple. And as this being said, I deal with more second order systems on the vehicle domain. And there are certain commands that, not necessarily always I want to track any arbitrary time varying commands, but there are certain set of commands that I want my system to track. Then I used an integral approach. This is one reason. Second reason, the controller types 1 and 2 can initially hit the system hard. Because simply look at here. You have K1, and let's say you are using a large K1, which is related with your position versus mu1. Mu1 is an approximation of the command. Actually, you know what? I will directly use the command here. Let's say command is 5. Initially, you are at 0. So this becomes -5 multiplied by K1. If this K1 is large, you are hitting the system initially hard, which may violate your actuator amplitude constraints, which is it is a whole different video by itself. Anyway, so if you don't want to hit your system hard initially along the lines what I just explained to you, you use a type of integral terms. So you need to do shopping here. And for shopping, I'm going to show you today 3 recipes. The first one, if you only want to track constant commands, then you would like to use this particular integral. Well, if you would like to track ramps, like we take off, we landing, our aircraft is acting like a ramp command we would like to track, right? Our altitude increase and decrease with some slope. And when you do cruise flight, you basically maintain your same altitude. Your command is constant. So this type of a double integral becomes very handy for me for my applications. If I am not happy about the first command, constant command, if I would like to do more. Now you can take this list longer. If you put 3 integrals, you not only track ramp and constant commands, but also parabola type of commands, alpha t to the power of 2 type of commands. If you put 4 integrals to the power of 3, 5 integrals to the power of 4, it goes crazy like this. But mainly, first 2 are my favorite. Also, when you use an integral approach, I should say, as opposed to the controller types 1 and 2, it also gives a little bit robustness to constant disturbances acting on your system. So without using any robust and adaptive control, integral will give you also a level of mild resilience against such disturbances. So you know what, to make the long story short, I am going to pick number 2. I just need to pick one of them to illustrate how we design a control using an integral approach. So I am picking this candidate. Let's say I have a case, I want an aircraft. I need to do takeoff with some slope and then cruise flight. My command is constant, maintaining my altitude, and landing, also landing like this. So second controller looks like a good controller for me. So we want to work with this type of controller. And now I am going to show you the trick. First of all, when you have 2 integrals, start from the last integral, call it z1. Now, if you have 3 integrals, you're going to call it z2, the last one, then z1, and you go backwards. But right now, you will see what I mean when I'm done with this. I am taking the first integral, calling it z1. So I reduced integrals to z that equals to z1. So I have 2 first one integral looking equations. So I am going to take its derivatives. Z dot becomes z1. Z1 dot becomes x minus c. If you have 3 integrals, you are going to have 3 integrals with 1 integral. You need to take 3 derivatives instead of 2. The story goes like this. And now you have 2 extraordinary differential equations. Remember, your system was second order, so you have x1 that equals to x2 that equals to 0, 0, 0 u, but now you need to include z dot and z1 dot states to your state space. So when you use integrals, you need to look at not only your state space of your system, but your expanded state space. So z1 dot becomes x is x1 minus c, which is not included here. It is not a big problem. You need to have another matrix, which is plus 0, 0, 0, minus 1 multiplied by c. So you are going to have two more terms here. But for the sake of designing the gain k, okay, that term is not important. That's why I didn't write it here. So, you know, this result that I'm going to show you, as long as the pair A and B are controllable, you can always come up with gain k by using this expanded A bar, B bar. Of course, in this case, Q becomes 4 by 4, R becomes 1 by 1. And your controller, unlike the previous controllers, I haven't revealed the control structure at the beginning. I am revealing it right now. If you are using this, you will have two more states, and your controller will be minus K multiplied by position, velocity, and this Z1 and Z2 states coming from these additional dynamics. If you had three integrals, you are going to have 5 gains. Right now, we are going to have 4 gains. Again, if you have any trouble understanding what happens when you have 3 integrals versus 1 integral, let me know in comments, then I will explain. But you know, when you have, to make the long story short, if you have add one integral, like in here, you don't need to define z1, z dot becomes x minus z. So you have x1 dot, x2 dot, and z dot. You have third order system but we are dealing with this. So fourth order system. So if you deal with this, you are going to deal with fifth order system. So again, you can use pole placement or linear quadratic regulator, assuming A bar and B bar expanded pairs are controllable. Just putting it here, it will give you some gain. And this is how your controller will look like. You have derivative, proportional, integral, so kind of a PID flavor plus double integrator that is more than a PID. So I think here you will need a numerical example. So this is how you design. First of all, you have a second order system, x dot equals to u, or in state space like this. When you use integral approach, you need to include z and z1, as I just explained, two additional dynamics coming from here, representing integrals. My expanded state space will have 4 variables. This is my initialization, my integral initialization, almost more than 99% 0. And this is our A and B that we established from the expanded pair. I am just using first the most basic 1, 1, 1, 1 for Q and for on 1. And the rest is recording and plotting. If I simulate this system, this is how it does. I initially launch the system. The red dotted line is my ramp command, then it becomes constant. It tracks. Then around 10 seconds, it changes to a constant. It still tracks. Again, I didn't tune it to do, you know, to improve the transient response. Apparently, I am using the world's most basic QNR, just identity and one. You can fine tune a little bit. I didn't spend a lot of time, but if you choose Q to be diac 150, and if you reduce R to zero point 0.1, you can make this converge faster with less overshoot as compared to here, more than 50% less overshoot and much faster convergence. You can make the system track like this. So anyway, to make, I think we are ready to wrap up. 3 controllers, which the last one I did not cover for first order cases, but important mostly. You can use for first order case, second order case, third order case, the same principles that you learn from these videos, then apply to in other systems. Um, For the last one, the integral approach is a bonus. I mainly prefer if I would like to track these type of commands. I don't necessarily need to track every time we're in command, but I am basically taking off cruise flight. You can do for landing as well. Different controllers. I hope these videos are beneficial to you. If you have any comments, let me know. Otherwise, see you in the next video. Thanks.